Is my screen visible to you all? Okay, so I'll start now. So in this week's tutorial, this is tutorial number 7. We will discuss some questions on Matlab that are based on sampling and reconstruction. So is this visible to everyone? This Adobe Reader?
Yes, sir.
Okay. So we'll just do these 3 questions, and this is basically to give you the gist of sampling and reconstruction. So let me start with question number 1. Okay, so the question number 1 is, we are given this signal and xat is equal to e raised to the power minus 1000 absolute of t, and we have to determine and plot its Fourier transform. All right, so we will first of all try to do it, determine it analytically, and then solve it in MATLAB. Okay, so first of all, this is what we have been given. So we know that Ctft of any signal which is of this type, e raised to the power minus a mod t, it is a two-sided signal for a greater than 0. So it is exponentially decaying also. And but because of, yeah, there is also a mod t. So it will exist on both the sides. So when I take the Ctft, it will be something like this. So I can do it with this uh, question that is given to us, and I can calculate the Ctftl. So it is 2a, a is 1000 here. So 2a upon a square plus omega square, capital omega square. This should also have been capital omega square, because in continuous time we take frequency, we represent frequency with a capital omega. That's the general notation. So that is it. Now, in the question, it is not given to us whether the signal is time limited, but we will consider it because, well, we have to evaluate this numerically, and for that we need to approximate the Fourier transform, and that is why we will take some t, let's say between. So in this case, I will take t from uh, minus 5 milliseconds to 5 milliseconds. So that is what I have taken. So that is why then when I have to calculate this capital omega corresponding to 5 milliseconds, it will be 2 pi by capital T, and that gives me 2 pi into 2000. So this basically means that when I calculate the CTFT, so the frequency response will be band limited. The frequency response is band limited at this frequency, right? So spectrum is between minus 2 pi into 2000 to 2 pi into 2000. Yeah, and so this is it. Now let's try to plot this Fourier transform in MATLAB. So, all right. So let me first define the time. I said that I am taking this signal from minus 0.005 to 0.005, or minus 5 milliseconds to 5 milliseconds. I can also give a decimation in between, which is basically how much uh, at how much time periods it will get evaluated. So I can take that as some small value. So I think this works fine. 0.00005. Now the signal is xa. This is the time domain signal. So it is e raised to the power minus 1000 into the absolute value of time. Right? This is the signal. So we can quickly plot this and see how it looks. So if I do plot first the time and then the signal, so this is how it looks. This is the signal. It is symmetric and it is real, right? Okay. So now let us calculate the CTFT. So for that, the first thing is that let me define omega max, which is the maximum frequency. So we calculated it as 2 pi into 2000, right? This is corresponding to t is equal to 0.005, right? And now I want to take these grid sequences for this frequency. So this is the maximum frequency, but I need to have a set of frequencies at which I will evaluate this, because when we are calculating CTFT numerically, we cannot do it from minus infinity to infinity. We have to take a certain uh, grid sequences of frequencies and evaluate at those values. So to do that, simple ways, let's say I am considering 500 samples on one side and 500 on the other. So 500, let's say, on the right right hand side. So I just define some capital K, which is 500, and I define a small k. So you basically MATLAB, because MATLAB is case sensitive, so this capital K and small k are different things. So I define it from 0, decimation of 1, up till capital K. And at these points, I will evaluate, I'll find out the frequencies. So I'll say that this frequency omega, capital omega, because we are in continuous time, is basically k into small k into omega max by capital K. So basically what it is doing is that when small k is 0, I'll have capital omega as 0. When it is equal to capital K, I will get omega equals to omega max. And in that way, I am varying this omega from 0 to omega max. All right, so we have obtained this grid sequences of frequencies, and now I can write down capital XA, which is the CTFT. So it is X of J capital omega. And basically that is, we will have to write the expression for CTFT. That will be the signal multiplied with e raised to the power minus j into t into omega. Now, one thing that you should note here is that t is a vector, right? T is a 1 cross 201 vector, and w will also be a vector. So what we can do is we can take their inner product. So I can put a transpose sign here. So that will, what will happen is that this will become a row vector and this will be a column vector. And we can get the values of XA as a column vector, right? So I'll quickly evaluate all of this, and you see that XA is a column vector. Oh, sorry, it's a row vector. So yeah, because T is 1 cross 201 and W is 1 cross 501. So XA, okay, we also have J here. Okay, Yeah, okay. So we will basically, this will first of all become a column vector and then we'll multiply it with W, right? So that is why we get XA as a 1 cross 501 vector. Now you notice that it says complex double. So that means that of course this XA will have real and complex components. So what we can do is that we can uh, say XA is just the real part of XA. That way, I do not have to worry about the complex part. Either way, when we plot the continuous time Fourier transform, we are interested in the real part. So I just take its real part, and but now you see that here I have taken frequencies from 0 to so we can quickly do that also. You can say that capital omega is, so for that we will use the flip LR function, which is an inbuilt MATLAB function. So basically what I do is that if I have a sequence, let's say T or 0, 1, 2, and 3, what it will do is it will make it flip them using this function and add a negative and 0. And then I will add to this the remaining frequencies. But since 0 is already covered here, so I'll start from the second position up till the end. So the end is 501 because there are 501 elements in W. So that way I have basically converted the frequency from minus omega max to omega max or omega min to omega max, whichever way you like to call it. And same thing I can do with the signal as well, because the Fourier transform will also be symmetric. So I can write it as flip LR. Now I don't need to put a negative sign here because this is the signal's magnitude, and I can plot it versus, and I can also add the positive part like this. So this way we have made our signal and the frequencies lying on both sides of the imaginary axis of the, sorry, yeah, on both sides of the imaginary axis. So now let us plot this, what it looks like. So basically these are the values of the Ctft, and now let's plot this. So let me just use the subplot to obtain uh, the plots, both the time domain and frequency domains plots in the same figure. So I use the subplot 2 cross 1, which means that it will give me a 2 cross 1 plot in which I am selecting the first one, and in this I can plot the time domain signal, which was t, and xa, which we already did before. And in fact, because time is in millisecond, what I can do is I can make this scale this x-axis. And now I'll select the second subplot. So for this 2 cross 1, I'll select the second one, and in this I will plot the frequency or the Ctft of the signal. So I have frequency omega and the signal xa. Omega is in radians per second. I can convert it into hertz by dividing by 2 pi, and in fact I can convert it into kilohertz by again dividing by 1000. So this is it. Let's see what this gives us. So this is how it looks like. So the first plot here is the continuous time plot. This is x80, the signal that was given to us, and this is its, I hope you can see clearly, this is its uh, CTFT. And so this is capital omega, and this is the real part of the signal, real part of the spectrum, right? So any Doubts so far? So any doubt in the first part? I didn't heard anything. So any doubts? No. Okay. Okay. So I'll move on to the second question. So this is how we have obtained first of all the CTFT, right? And in the second question, uh, we have this. We have now that we have calculated the CTFT. The second question says, first of all, we have to sample the continuous time signal with a sampling frequency of 5,000 samples per second to obtain the discrete time sequence. And for that discrete time sequence, we have to find out, determine, and plot the DTFT, which is x1 e raised to the power j omega. Okay, so first of all, uh, let us look at all, some things like, first of all, we have been given f of s, which is 5,000. So we can calculate the sampling time, which is nothing but 1 by f of s, sampling period. So it will be 0.0002. And previously we took the signal from minus 0.005 to zero point zero 0.005, or from minus 5 milliseconds to 5 milliseconds. So corresponding to this maximum time, 5 milliseconds, we can also find out n max, because for the discrete time signal, we will have some sequences n, right? Instead of uh, time is not a continuous quantity now, we have n max. So we can calculate n max, which is corresponding to the maximum time. So when we do sampling, we know that xn is nothing but the signal x sampled at n ts times. So from here I can calculate n as t max by ts. So the maximum time is 5 milliseconds and the sampling period is 0.0002. So when I do that, I get this as 25. So that means that we can have our signal from minus 25 to 25, the sequence xn, from minus 25 to 25. So that means we will use something like this. Okay. Okay. So let's go back to Matlab. And so first thing is that Ts was, we can calculate by 1 by FSS. So it was 0.0002, right? And N we just calculated should be from minus 25 to 25, so that the whole signal can be plotted. Then I am okay. So now let me write down x of n. So x of n will be, so I had denoted the continuous time signal by xa. Let me just use x to denote the discrete time sequence, which is obtained after sampling. So it will basically be exponential, just the same thing as before. So it will just be like xa only. Only thing is that this t will be replaced by nts. So this becomes exponential of minus 1000, which is an absolute value of, so I'll replace t with n times ts, right? So this is the sequence. And now I can also try to plot this. So if I say stem, so because it's a discrete time sequence, so I'll have to use stem instead of plot. So the x-axis is basically uh, n into ts, right? And I can convert it from, because t was in milliseconds, so I was multiplying with 1000 to scale the x-axis, and then y-axis will be the signal x itself, right? So let me try to do this. And in fact, let me first plot the continuous time signal, and then I will hold this plot, and on this I will plot this. discrete time sequence so that we can see how well sampling has occurred. So as you can see here, this was the original signal in time domain and we have sampled it, and these are the values at which we have sampled the signal, right? So let me now try to find out the DTFT of this x of n, which we just plotted. So first of all, let me define small omega, which is the frequency in the discrete time. Now we know that small omega varies from minus pi to pi. So just like we did in the previous case, I will again use uh, small k and capital K in order to find the finite grid sequences where this omega will be defined. So the maximum value will be pi, and I can write it just like the previous case. Small k divided by capital K. So when k is 0, I will simply get omega equals to 0. And when k is equal to capital K, I will get omega equals to pi. So that way I will get omega varying from 0 to pi. And then I can later on flip it and convert it into from minus pi to pi, right? So before that, let me just write down the signal, the TTFT, which will be this small x, that is x of n, multiplied with e raised to the power minus j n omega. So minus j into n transpose because it's a vector, and then I again multiply it with small omega, which is the frequency. And this will give me capital X, which is again a vector, right? Now I have got the frequency and the value of the signal spectrum. So but this is from 0 to omega. Now I need to convert it to minus omega to omega. So again, just like the previous case, I will use the flip lr command. I will say minus flip lr of w in order to obtain everything in the minus pi to 0 range, and then I will say omega from, or w from, 2 to k plus 1, right? K plus 1 because uh, 0 to k plus 1 there are, if it is going from 0 to k, then there are k plus 1 samples. So this is omega. Similarly, let's do this for x, capital X. So here I'll do flip LR again, capital X, and X again going from 2 to K plus 1. And because X is a complex signal, I only want the real part of it to plot it. So I'll just do X is the real of X so that the imaginary part will be neglected. And I can say, let's plot uh, x-axis, which is omega, and X, capital X, right? So we have already seen this part. Let me now draw this DTFT. Oh, I think, oh, it didn't, it just plotted on one side. Okay, why is that? Let me check it just to see why this is happening. So omega starts from 0. I replace omega with this part, but it's still from, now it's, Just a second. If anyone else can point out my mistake, then that will be really helpful. Well, this should not have happened because omega is from, so this part is 1 cross 501 and this part is empty, which it should not have been. Okay, I guess I need to define k once again, but k is fine. Oh, okay. Oh, I got my mistake. This should have been capital K. Okay. Yeah. Sorry for that. Yeah. So this is the signal finally. So the mistake I was doing was I was taking this as small k, but small k is actually this whole vector. But I wanted it to go till the end, and so I should have used capital K. But anyways, I'll plot it now that it is rectified. So yeah, this is the CTFT. Sorry, the DTFT. So you see that this is the DTFT, and previously when we plotted the CTFT, which was this, let me just write some other figure and I'll plot it here. So this is the DTFT and this is the, wait, I think no, sorry, I plotted the signal. There is no W. Yeah, so I'll just show this one. So this one on the bottom is the CTFT and this one is the DTFT. So you see there isn't much difference. They look exactly the same except for the magnitude, and that is because we have, that just shows that we have taken enough samples in order to convert the signal to the discrete time sequence. So that's it. This question is Yes, so this was this question. Question number second, we have found out the plot for DTFT. Is there any doubt here? Okay. Okay, I'll move on to the last question. Now we have got x1n, which is the sequence, and we have to reconstruct the signal x80 and comment on the results. Okay. So for this part, we let's recall that whenever we have to reconstruct a signal from its sequences, sampled sequences. So ideally what we do is that we pass this signal through an impulse. We first convert it into an impulse train, and then we pass it through a low pass filter, an ideal low pass filter, and we will get X80. Uh, we will get X80 back. And this ideally, when we are using this ideal low pass filter, so the interpolation formula can be given as this. So we can say that this two-step procedure can be uh, written like this, where the sinc function is used. This can be represented by the sinc function, and this is also known as the interpolation formula. And this sinc function or sin c function is basically sine pi x by pi x, right? So this is how we do it. And but you see that this is valid for an ideal low pass filter, or when we have an infinite number of sequences, or infinite number of, yes, infinite number of time samples at which we have the value for the sequence. But ideally we don't have that. That cannot happen. So because it is not practically feasible to have ideal interpolation, and that is why we will have to find out a way to do it numerically. So to do that, we will make use of the Matlab function, which is sin c function. Now we will use this function to reconstruct x80, and we will see how that can be done. So we have x of n, and yeah, so we have x of n. So if you take f of s, which is now the sampling rate at which we will obtain, basically is the sampling rate of the or the sampling frequency of the reconstruction filter, then I can simply take it as 1 by ts, where ts was the frequency with which we had originally sampled the signal. Because we know that there will not be any aliasing, because for we have taken, when we sampled, we took the frequency as 5000 samples per second, which is greater than omega here, which was here, right? Omega or capital T was 2000, or it was, we can say that the capital F would be of the x80 was 1 by 2000, 1 by 2000, and that is why f of s is at least twice of that. So since this is uh, fc was 2000, we have selected f of s as 5000, which is more than the Nyquist rate, because Nyquist rate would be 2 times 2000. So we know that there is no aliasing, and so we can choose the same f of s here also. And let me just define this nts, which we already previously did, but it will be n into ts, and I can then directly put it in the formula. Now time I am defining just like I did before. In fact, yeah, I think this will work again. I can just take this time. Now, so now in order to do this reconstruction in MATLAB, I'll try to write out this equation, which is the ideal reconstruction. But now instead of having infinite number of sequences, I want to do it for finite number of sequences. So that means that there will be some error between the signal which we obtain after reconstruction and the original signal. And because there are finite number of these sequences, I can actually do this by a vector matrix multiplication. So I know that xat is these values of x evaluated at time from 0 to t max, or rather from yes, from 0 to t max. And this x of n has n going from, so let's look here. So we have n 51 number of n's, and we have 201 number of t's. So what that means is that I can say that it is going from xa0 to xa201. So this is the 201th entry. And similarly, x of n is will be evaluated at 51 values. So first of all, let me write the expression and then I will explain it to you what it means. So let me just say that the reconstructed signal is xr, which is the signal x of n multiplied with that sinc function, right? Just like in this equation. So it is sinc function. So now I'll try to do it with this matrix, vector matrix multiplication. So I have f of s multiplied with, so I have taken a vector of ones. So all the value of this vector is 1, and I have taken it to be equal to the length of n, which is 51, and it's so there are, it's a column vector, so it has 51 rows and 1 columns. And with this I'll multiply time. So this way I have got fs into t, and now I need something like nts, right? Because there we have fs t minus nts. So I have written fs, this is t, I have multiplied it with a vector of 1 minus nts. I'll take its transpose because nts will be a vector. So nts is a 51 entries column vector, and I will multiply it with again an vector of ones. And let me first write it down and then I'll explain what it means. Okay. So what I've basically done is, so this sync fs t minus nts. Let's say first of all we are interested in finding out xa at the continuous time index of 0. Now in order to do that, I will just put t equals to 0 in this expression and I'll get this part where n is from minus infinity to infinity, x of n, sync f of s, I have replaced t with 0 and I have got this minus nts. Now I can write it out as a sum of from all n, right? Here it is minus infinity to infinity, but numerically we have n varying from 0 to 51, right? There are 51 entries of n varying from minus 25 to 25, which we originally took. So we want to evaluate n at all these values. So I can write it as x at minus 25 sin c fs minus 25 ts and so on up till x of 25. So that will just, when I add all those values, I'll get xa of 0. Now I want to write this whole expression or each of these sums as a vector matrix multiplication, right? So what I do is I say, let me write down all these elements of sync fs minus nts in a in a column. So here I have f sync f of s n min of ts, which is the minimum of n, which is minus 25. And I will keep on writing down these elements entries until I reach n max ts, which is the last entry. Now I want this to be multiplied with x of 0, or x of n min, which is x at minus 25. And when I multiply each of them with, uh, or when I multiply x n min with this and x n max with this, and I sum them all, I will get x a0. Similarly, for the next one, what I do is, instead of taking t is equal to 0, I take t is equal to 1. And the next column will be t is equal to 2, and so on. So the last column will be t max, which is the 201th entry. And for that, I will again multiply it with this vector. And in this way, I have written, what I'll get is this whole vector of xats evaluated from 0 to t max. So in this way, to obtain each of these, I know that I needed the product of uh, one entry of x with a sync function. So I have written it as a vector and vector multiplication, and then I have put all these vectors in a matrix, and that way I can get xa. So this whole product and summation gets converted into this vector matrix multiplication. We can also check the dimensions. So this is one row, and there are number of columns are equal to the length of n, which is from minus 25 to 25. It was given as 51. Similarly, the length of this will be, so it will have the number of rows equal to n, because n is moving from n min to n max, and the number of columns equal to the entries in t, which is from 0 to t max. So in this way, when we do this, we get xat completely back. And that is what I have done here. I have first of all multiplied it with a vector of ones in order to convert it into a vector, and then I have done the same operation. And if I plot the signal versus the time, so this is the reconstructed signal. So it looks like this. So you see that it's not as smooth as the curve that we initially had. The curve that we initially had was small xa. So if I plot this on the other hand, in let's say some other figure, just so you can compare. So you see, this is the figure that we obtained after reconstruction, and this was the original figure. This was the original signal, and after sampling and reconstruction, we have obtained this one. Now we can take more number of time samples, and we can obtain a much smoother curve, but even this is quite nice curve. And clearly there is no aliasing, which we had already seen, considering the fact that we have taken the sampling frequency much larger than the Nyquist rate. So in that way we can do this. So one thing that you can try is that you can take this fs as, let's say, 2000 samples per second, or something like that, or even 3000 samples per second, and you will see that you won't get this a curve like this. You will get a lot of the curve will not be as smooth, and it won't match the original function or the original signal. So finally, we can do one more thing. We can look at how much is the error between the original signal and the reconstructed signal. So I'll define some error, which is basically the maximum absolute difference between the signal x R, which we have reconstructed, and the original signal, which was XA, sorry. Yeah. So when I do this, so it says 0.0363, which is approximately 3.63%. So this is a considerable. This is not that much, and that is because of the way we have sampled above the Nyquist rate. So this is it. This was the last question. Are there any doubts? Okay, sir, will you be sharing the code? Yeah, sure. I'll share the code with you. Uh, Maybe in the classroom, or I'll share over mail. I'll share the code with you, no problem. And I will really suggest you to try to tweak the parameters in this code, because, for example, the sampling frequency and so on, so that you can observe for yourself what happens other when there is aliasing. So the case we have seen, there was no aliasing, so we have obtained a very nice figure, but that's not always the case. So uh, please try it in your spare time. And yeah. So are there any doubts? Okay, so I think if there are no doubts, then we can end this meeting. Thank you. See you next time.
Thank you, sir.
Thank you, sir.
Thank you.